Hello, my name is Evgeny Belyaev. I'm from University of Information Technology, Mechanics and Optics, St. Petersburg, Russia. And my presentation is dedicated to fast recovery of compressive sensing images via multiple thresholding operators. Compressive sensing is a framework which can be used for development of new chip image sensors which observe a small number of random linear measurements instead of all image pixels. For example, it could be 10 or 20% of measurements. As we know from Nyquist-Shannon theorem, a linear reconstruction by inverse transform cannot, in general, recover the signal from such small number of measurements. But as it was shown in Donoghue, Candice, and Romberg's works, if the signal is sparse in some known transform domain, then a stable reconstruction is possible. However, a high computational complexity of the reconstruction is still an important issue restricting the use of compressive sensing in real life. In this work, we propose a heuristic recovery approach which allows to achieve a good trade-off between the complexity and the reconstruction quality, and we hope that it could be useful for real-time applications. Let us consider a two-dimensional image X, size of n by n pixels. In compressive sensing, the linear measurements Y are acquired by phi by X, where X is a vectorized version of the image and phi denotes the measurements matrix. And this ratio is known as sensing rate. For reconstruction, we assume that the image has a sparse representation in a known basis, where omega is representation matrix and theta is the sparse vector of the transform coefficients. As an example, L1 norm could be considered as a sparsity metric. Under this assumption, the recovery is formulated as a searching for the sparsest vector theta which satisfied this equation. As an example, we use the following sensing model. An image is observed by two kinds of measurements. First, we take scaled coefficients of a wavelet transform. In practice, it corresponds to downsampled version of the image. Second, we take a small number of noiseless transform coefficients located at random positions. On the right side, you can see the recovery using inverse transform in assumption that all unknown coefficients are zeros. One can see that this simple approach cannot provide good quality of reconstruction. In this work, we reconstruct the image by solving the L1 minimization problem using iterative soft thresholding. An image at iteration k is estimating using this equation, where soft means soft thresholding operator with threshold sigma k, and this one is image estimation obtained at previous iteration. The initial estimate is zero vector or an image provided by any other recovery method. The soft thresholding operator for an image X includes three main steps. First, a sparsifying transform with matrix omega is applied to calculate transform coefficients. Then soft thresholding transform coefficients are calculated using this equation, and finally a soft thresholding image is calculated using this thresholding coefficients. As an example, two-dimensional discrete cosine transform size of L by L could be considered as the simplest and fastest sparsifying transform, but of course it has quite low reconstruction quality. In order to improve it, we could memorize, for example, from image coding framework, that large block size is efficient for flat areas, while small block sizes could be better for areas with many details. In order to improve the recovery performance, in our previous work, we proposed to calculate thresholding for several block sizes at each iteration and then compute an average using this equation. This approach provides much better recovery performance, but unfortunately in this case we need to compute transform several times instead of one as in original scheme. This slide shows comparison between different recovery approaches. On the x-axis you can see the number of iterations, and on the y-axis you can see peak signal to noise ratio which is the most popular image quality metric. This curve corresponds to the cases when we compute thresholding only once using single DCT, for example 4x4 or 8x8, and this curve corresponds to the case when we compute thresholding 5 times using listed DCT and then compute averaging. One can see that this approach is much better than the case when we use the single DCT all the time. In the same way, we could use 8x8 DCT all the time, but we could change the shift of block grid, for example by vector -1, -1, or 1 by 1, and so on. In this case, we can see that this approach provides even higher performance than the just averaging of the different transforms. In order to reduce the computational complexity, in our previous work we proposed to use at each iteration a pseudo-random value for block size, chosen with uniform probabilities from some set. For example, such set could be like from 4 to 64. In other words, we perform only one randomly selected transform at each iteration. So here we can see that this random approach provides similar performance compared with this averaging approach. And here we try to use even larger set of different shift vectors. So in random case we use vectors from -4 to 4 in each dimension, so it covers 81 different possibilities of the grid shift, but while here we use only 9 different possibilities. That's why this random shift provides even higher performance than the averaging. In order to achieve even higher recovery performance, we could use more complicated thresholders. For example, block matching 3D filtering, well-known image denoising filter, can be used for recovery at each iteration. BM3D exploits both local and non-local similarities of images and, as a result, achieves much higher quality of reconstruction. However, the main drawback of BM3D is its high computational complexity caused by block matching, 3D transform computation, thresholding within 3D transform domain, and other operations. In order to achieve a good balance between the complexity and the quality of reconstruction, in this work we propose to combine the recovery based on 2D DCT with random shift and BM3D. During first I1 iteration, only 2D DCT with random shift is used. At the remaining iterations, we run BM3D with probability rho and 2D DCT with random shift with probability 1 minus rho. For our experiments, we set I1 50 and rho 0.2. In other words, we use BM3D only 10 times in average. This curve corresponds to the case when we apply BM3D at each iteration. So in order to achieve this level of quality, we need to run BM3D 100 times. And a black curve corresponds to the proposed approach where we run BM3D only 10 times in average. And you can see that proposed approach provides quite close quality to this approach where BM3D is used all the time. Here you can see visual comparison of different recovery approaches. This image corresponds to the case when we apply thresholding with 8x8 DCT all the time, and it provides some basic quality and takes around 12 seconds in MATLAB. This image corresponds to the case when we apply random shift all the time, and you can see that it provides much higher quality and it takes the same time. This image corresponds to the case when we are applying BM3D, and at each iteration you can see that it provides much higher quality of reconstruction, but it takes 52 seconds in MATLAB. Here we need to notice that BM3D used here is already accelerated using different techniques. And this image corresponds to this proposed method where we apply BM3D 10 times in average. And you can see that quality of this image is quite close to BM3D, and it takes significantly less time for reconstruction. So we hope that the proposed approach could be attractive in real-life compressive sensing applications. Thank you for your attention. You can find more information about my research and my projects following this link.